Okay, it's recorded. Share screen, okay. And then this and that. Okay, well, sorry. Okay, so the interface is pretty much a very straightforward. And again, you just enter this old value, say epoxy, for example, epoxy, Young's modulus is 3.4, and as a Poisson's ratio is the 0.3, you can say. There are another column for this. Well, at this point, you don't have to worry too much, but could be very useful functions which you may need to know. This is the probability generation. Say you enter average and standard deviations. All the variables can have a probabilistic distribution. Any variable, especially material property, they are not just uniform. So let's say you have an average value, 3 point whatever value, and you do have some standard deviation. This probability, Excel has its own function. It's called probabilistic generation with some nominal average using the random variables, and this average and standard deviation is automatically generated. This is the value whenever we enter. As you can see, there will be a certain value recalculate using this standard deviation. But I don't want to go too much detail. All you need to do is just enter this value, deterministic value, and you will get this output. So say fiber property, okay, fiber, very high stiffness, even higher than steel. Steel, Young's modulus of steel, what's the value? 200 gigapascal, right? But the fiber is easily 250 gigapascal. AS4, IMs, very high stiffness. Even T700 will be higher than 200. So let's say 250 and 3.4 gigapascal, which can be very typical value. And carbon, transverse-wise, the stiffness is very low compared to in longitudinal directions. The reason is that do I have that? I don't have that one. Oh, here. See, this is the very good to know. This is a carbon fiber, and carbon fibers, all the carbon atom array is the this hexagonal. In this way is very strong, like a CNT, carbon nanotube, or graphene. And carbon fiber is just a layer, and all the arrangement in the longitudinal fiber direction is aligned this way. So as you can see here, transverse direction is much weaker than in longitudinal directions. Okay, but in glass fiber, as you can see, glass fiber is pretty much isotropic. So glass fiber, you would have all same material property everywhere, isotropic. But carbon fiber itself is anisotropic. You can imagine this kind of a layer. It's like a graphene layer rolled like a cigarette rolling. That is the carbon fibers. Okay. So, well, it's not easy to precisely get this value, but you will see this transfers, which is not so important in predicting our value, but you can find this value from the references. And this is the fiber volume fraction, a very important value, 60%. And others, like the resin, tensile strength can usually epoxy is about 70 megapascal, and sometimes very high can reach 100 megapascal. Strength is always a mega, and stiffness better to be a giga. And compressive matrix. Compressive strength is about 140. So this will be epoxy typical value will be at 70, and others. Let's just fiber strength, which is also important. Fiber strength is very high. It can easily 3,000 megapascal. Tension, fiber tensions, and compression can be low. Well, compressive strength is usually controlled by the fiber buckling, but in this micromechanics, we don't consider that kind of advanced behavior. Okay, those are pretty much the important value, and as you can see that, pay attention to these values, and you can see how these values are vary if I click this button, okay? In the PC, it would take just a second, but in here laptop, it takes a little longer. But as you can see that the stiffness can be 150. Well, simply 150 comes from this a 250 fiber stiffness times fiber volume fraction, 60% is roughly 150, right? That follows rural mixtures. But again, this all the calculation is not the simple rural mixture. It is from all finite element programming, and I will show you whenever I click. Look at this background and all kinds of calculations, input file and output file generation and finite program call and in and out and then delete. I better. I know this why this is slow because this Google Drive. So when you run this, you better turn off all the cloud. Okay, now the disk. Okay. Okay, so again, very useful. You just copy this value and copy into your Excel tools. Well, for last 2 weeks, I believe you simply program using micromechanics. So starting from this value and through rural mixtures, which we studied 2 weeks ago, and then you have this one. Will be very nice to compare these values, which is can be compared with your simple rural mixtures. One study I add here is a quick chart. Quick chart here, the same quick chart we used to use. Say we changing these 5 volume fractions as the input. Input comes from this variable. So what we gonna do is that we keep changing these 5 volume fractions. We change this value and it goes to their input, and then we will get this output from this. Okay, so this is the input file. I mean the name of the worksheets. I will just call a class, and then using the quick chart. Now, 5 volume fraction, let's vary from 0.4 to 0.7. Well, 0.7 is very high 5 volume fraction, but some we can achieve with the autoclave. Okay, and 0.5 is about average value which you can have achieved with a regular RTM. And step value, let's say 0.0. To 5. So every step we are covering from 0.4 to 0.7. Okay, and then what it does is we change the 5 volume fraction from 0.4 to 0.7, and every value we get all the ply properties and stiffness and strengths, and then list them, and it will show us all the output results. Well, it will take about 1 minute. Okay, so let's say that is the what the outputs in our class share folder. You will have this all the PowerPoint and very simple procedures, and you will get the outputs. Okay, so for example, fiber IM7 and resin 8552, very high stiffness, not this much high, but anyhow, this is one, and then this is the material property you would get. And still on. And as I just mentioned, there is the, you don't have to try, but just for your reference, over here, there's a standard deviation and things. And this concept of average and standard deviations really need to be understood well. I mean, for you as engineers, always input has a certain probabilistic distribution. Could be normal distribution, any kind of a probabilistic distribution. And through models, imagine that we have a micromechanics model, and we would have a output. Say input resin stiffness, okay, fiber stiffness can have not just a uniform value, it have some variations, right? But this is a fiber property. Now here is the phi property. It could have a certain variable. And this input can have many, many different probability distribution with certain ranges. This is standard deviation, and this is average value. And we have a tens of these. So what will be the output? This is the concept of the Monte Carlo simulation. And consider all kinds of possible choices and what would be the distribution. This is really good to know in real design concept. This is the Monte Carlo simulations, and Excel has that kind of functions. So all you need to do is input, average, and standard deviations. And through model, in this case, micromechanics, you will get the ply stiffness and ply strength. Okay, this is a probabilistic sensitivity. And again, using this concept, effect of defect on ply property. What does it mean? Well, 이게 없앨 수가 없나? Okay, so all these, and then we get the ply property, but again, we can have a little bit of a void, little bit of a degraded material property of the epoxy, I mean the resin and fiber. And so this probability distribution will be very useful to simulate those kind of defects. And here, a variable value varying. Let's delete these things. Say the shear property and all kinds of Young's modulus, and here what is this? Okay, X is the fiber directional strength, and depending on the fiber volume fractions, and it varies from about how much? 1200, 1200 to 2000, very high, and also Young's modulus. Where is the EX? But anyhow, this is the a material property dependency on fiber volume fractions. Okay, this is just generated, and so you can use this quick chart, or you can just enter the value and then click this button. And this sensitivity, if you click this one, and rather than starting this value, we start from this average and standard variation, and then calculate and comes, and then output will have this kind of distributions, and then output will be very variable, and that can be also calculated. So for those who are interested, please try this, and I'm sure you will learn a lot. You know, probability distribution is really important, especially in the real design world. And well, this is the same slide explaining the same concept. Okay, all the input is not the one value. You have some probability distribution. What will be the output? What kind of distribution we will have? The reason why this concept is so important is that, let's say we like to have some keep some quality of this output. Let's say we like to keep this value to what that range is. Well, in narrower, if you want to control the quality of output very narrowly, if the manufacturing process is so expensive, right? So if you know the sensitivity on this output from this input, is very useful. Okay. This is some example. Okay, which were from these tools, and man, this is bothering. 이건가? No. This is the volume fractions, average 0.6 and standard deviation 0.03, and then output of the EX is this. It varies from 150 to 189, and average value is about 170. Okay, and to get this one, you need to iterate a lot. Okay, iteration, number of iteration you can specify here. And you can increase numbers. But okay, so that is the brief idea about this SF Gen. I hope you like it. Okay, any questions on this tool? Oh, there are a lot of another study is the effect of a void. Effect of a void. Let's say there is the one terms called void fractions. Here, let's say 2%, which can be also input, and the void can be also have a certain probabilistic distributions, and it's not easy to measure, but about 2%. And depending on the manufacturing process, RTM can be like a 2%, and autoclave can be less than 1%. And then you can see the effect of the void as well. Well, okay, that's the a brief introduction of this SF Gen. I hope you try this, and you should be able to learn. I mean, run these tools because your homework will be such that you need to use these tools. Okay. Now let's move to another tool, which is the 3D beam. And the 3D beam is much more powerful tools than classical laminate plate theory. And I just want to give you an idea about this output. I will briefly introduce the structure of the 3D beam, and this is a post-processing. After you calculate using 3D beam, for example, this is the elliptic cross sections, and you can This is, by the way, real output from, again, finite element program, but all the user interface and programming in the Excel. And you can see that, you can see you have a stresses, a bending, and well, this shape is very short, but I just picked the one on models. But for the 3D beam, application of 3D beam is the structure which has to be relatively long structure, relatively a beam. Then accuracy will increase. The short, accuracy will decrease, because all the theory is based on the beam theory of the composite. Composite beam theory, by the way, is not quite well established. It's still under development. But this one, well, we developed for many years, and it's good to know and good to compare, good to understand the composite behavior. Okay, let's say we have a 10-minute break, and then we'll continue to this tour. Okay. Okay. Well, very happy to share this tool with you. Well, this is again based on Excel, but do not underestimate the capability of this tool just because of it is in Excel. Again, the Excel these days, the languages and is not so important. You can use your MATLAB or Excel or C#, Java, whatever language you feel comfortable. These days, the computational power is so high, so you can just need to know at least one developing tools. Then you can do many things. You don't need to learn many high advanced tools. Anyhow, as I mentioned, you can imagine that there are, I don't want to go in detail, but here is a hundred thousands of macro line for the FM source code, and sorry, composites. Sorry, some slide is in Korean, but it's not so critical, I guess. Okay. So this theory on the layered composite. This is what we covered. Say we have a layer of a UD with different angles and thickness, and this is all the load, and this is all kind of coordinate systems, right? And these kind of layered structures can be applied it is a theory in general, not only for the composite material, but also well, electronics. These days, you heard many times OLED screen, TV, which is the also consists of a lot of layers, and that can be also analyzed using this tool. This is just for your reference, and not only also UD, also oven, and so on. Another one we like to cover in this 3D beam is mainly for the beam structures. Say we have a beam. This kind of a composite beam usually made of a pultrusion. Pultrusion is like a uniform cross sections and pull, and you can have many different fiber angles and materials, and you can have a certain sections, sometimes closed like a we call box beam or tube with the circular cross sections, and industry-wise we use these kind of beam structures a lot. Now we like to know what kind of response, say subject to a certain load, and how much deflections and how much is stress, and so on, to be able to design sections and thickness and angle and so on. And for this kind of a flat plate, you can use the tool you've been developing. I mean, this is the Excel we studied together, load, layup sequence, and all the theory, right? And so we can do this kind of a parametric study using the quick chart. Be sure to have a quick chart in your Excel tool, okay? And quick chart, and you can see the effect of Young's modulus and effect of Parsons and so on. Now, as I mentioned, so point is that we have a flat plate-like structure. We have a beam-like structure. So using your Excel, we can study flat plate-like structures. Now we like to cover the beam-type structures. Oops. Well, this one I briefly presented to LG Electronics. They are much concerned a lot about developing, the vacuum these days, vacuum cleaner, and the weight of this vacuum cleaner. I'm not supposed to say much about this, but anyhow, this can be a tube, can be, say, made of a composite, and so how much you say we can lift here different angle, and you can see how much this tube can be subject to a lot of load, and the user need they are very sensitive to weight. So the application of this 3D beam can be cover many different applications. Wind turbine blade is one very typical structure, so we can analyze using this 3D beam. Imagine this one long blade, okay, long blade, which is pretty long. Well, how long is pretty long? This is about 70 meters. 70 meters. Now they are targeting at 100 meters. Just one blade, 100. So diameter is like, a little less than 200 meters. Huge blade. And the total weight will be about 30 tons, and significantly. Where in Korea, wind turbine blades, wind energy market has been pretty much down for last 5 years, but now the government really encourage industry to toward this business. So I expect that the wind generation and business will go up again. I'm pretty much sure that. Anyhow, in Europe, in German and France and UK, they are the industry or technology of a wind turbine blade is pretty much advanced. And especially 2 weeks ago, I've been in China, and even China, there are hundreds of different companies who like to develop the wind turbine blade, many different concepts. The main idea I like to introduce to a wind in business, China and Europe, is that I call a synergic skin. And this a pressure side and suction side. We use a different material. One side carbon, the other side glass, or different angles. A very interesting design, in my opinion. And industry like that, they like to try. If you are interested, you can find the several papers which been published. And also one application will be a wing of this airplane, which I can show you how easily can be modeled using these tools. And utility pole is being commercialized by BASF and now installed in India and China. And yacht, while this mast and all kinds of structures, all made of composites, 100%, and each component can be analyzed using these tools, and all the pipe subsea. So anyhow, as you can see that the geometric wise, the length is much longer than cross section, which this kind of structure is categorized as a beam. Beam has a very special structural behavior, regardless of material. So we make use of such a behavior, okay? And again, the theory is beyond our class, but as I mentioned, this theory is based on the finite element program. So let's say we have a 3D geometry structure like that. If we analyze as they are, the computational is very slow and modeling wise very difficult. And whenever you want to change a certain variable, it would take a long time, and complicated modeling doesn't mean it's a good model. Sometimes causing inaccuracy. So anyhow, in beam analysis, each section, we call this one is the section, okay? Each section, we model each section as a one element with two nodes. In FM, we call node, and one is the element. So one element with two nodes, and so on. So each element have a different section shape, and each section, as you can see, you can have any arbitrary cross sections, and you can have a airfoil, you can have a box beam, you can have a tube, and you can have any sector, any part here along this. You can have arbitrary layouts, changings. Well, I didn't say much about it here, but these tools also can be well applied to automotive parts, like driving shafts and so many. So this is the a flow chart in 3D beam. You don't want to go too much detail in theory, but understanding whole structure will help you a lot. Understanding this tool and design procedures. Well, starting from input, as you can see, is a material property, layout sequence, cross sections. Material property like the EX, EY, and all the strengths. The applied property is the material property input, and layup sequence, you know, pretty much same as the classical laminate theory. And in addition, we have extra information, cross sections. Cross section means, you know, these cross sections. So the theory we have covered so far is apply only one shape here, okay? You can imagine that you have a one, this can be a very small plate. This can have a certain layup sequence and many plies and many different angles. And this will subject to a certain load, incline and bending. And this is the classical laminate theory. Any tool, any FM will follow these procedures. Okay, so the theory applied to that element is already we understood. Okay, and good thing is that we have a many different angles. I mean, the layup sequence can vary all over this section, all over this way. So this tool, what it does is the combining all the layups and information and construct this section bending stiffness. This one would have its own, you know, the bending stiffness, right? And torsion stiffness. And that's basically what it does. And I can give an idea of these tools and 3D beam. They consist of many worksheets, as you can see, many worksheets. And one of the worksheet is called MIMAC CLT. This CLT is the format is exactly same as we have studied. See angle, thickness, and ply numbers, and all the EX, EY, and strengths. And see Q11. Now you understand what is Q11. Now you understand what is A11, B11, D, and all theory. And on axis, off axis, SIU, and all kinds of failure index. So what it does is that, say we call one element number means that we have this is the element number one. One element would have also 1, 2, 3, 4, 5, 6, and so on. So the program, what it does is that call element number, and the other one is the we call it sector number. So 1, okay, 1 and 2, and it automatically call all kinds of informations. As you can see, information is automatically called, and all kinds of load as well. Other than that, the procedure is exactly the same. As you can see, the output, well, in this case, I consider many layup, but which you can also do that. You can see here is the ABD matrix. Okay, ABD matrix, which is exactly same as the theory we cover. Well, there is a little bit of extra term, but don't worry. Okay, so this is the key worksheet which is being used in this final element program. So the material layup and cross sections, which I will explain further. And since it's the FEM node with a nodal coordinate, element with a nodal connectivity, coordinate and connectivity means that, okay, we have a node always XYZ component, element consists of a node 1 and node 2. And element 2 have a node 2 and node 3. So these are called nodal connectivity, and this coordinate is called a nodal coordinate. So any FEM program has two fundamental information. One is the nodal coordinate and element connectivity. In this 3D beam, after you run it, as you can see, this will be the output from this Excel. And as you can see, it consists of 960 nodes and has a node XYZ. And you can see all kinds of information. Well, we don't have to worry. And another important information is that element connectivity. Where are they? Control find element. Okay, here. Element has the element 1 consists of a material number and material property, and then 1, 2, 3, 4. 4 is the, since it's a shared element, we have a 1, 2, 3, 4, and 1, 2, 3, 4, and so on. Well, I hope you're interested in developing final program. Or if you look at the Abacus info file or NCC info file, any info file will have this nodal coordinate and element connectivity. That needs to be understood. Okay. Well, I'm trying to not to go in detail, but and nodal connectivity, element connectivity are automatically generated. You don't have to worry after you define the cross sections. And boundary condition always, you know, the structural analysis always start material property, geometry, and load. Load consists of a boundary condition, certain fixing point, and you apply the force. Those are input. And then output will be displacement and strain and stress and many information, including a vibration mode, natural frequency and natural mode, which is also important to understanding general structures. Okay, here is the some theory about the FEM. Well, a lot of equations, and I know you don't like it, so let's skip. But FEM, please keep that in mind, always starting from the displacement assumptions. Displacement, and then next step is a displacement and strain and stress, and then virtual virtual finite element and formulation, you know, minimum potential energy theory, and we get these governing equations. M double D dot plus K and D. Static K and F, D is the all nodal force. So K matrix is sometimes as big as number of nodes, number of unknowns. So anyhow, that's the procedures, and I briefly explain about these the structures and even worksheet, but don't need to worry. So conceptually, here we have any cross sections, and each cross section have the I call this one that I just call sector. Okay, one sector you can think that is the laminate, and laminate can be a sublaminate